Okay, guys, good morning. So, let's continue from where we stopped. I don't know why this thing is up here. But I hope you guys are studying this chart, okay? This is very important. This chart is very important. Very, very important. Make sure you know what those reagents can produce. That's not where we're supposed to be. I don't know why I'm here. Okay, so we're still talking about the exception to the ZF rule in terms of E2 elimination. We said the Joseph rule as a general rule says that the alkene that is most stable is radioselectively formed. Okay, that's what the rule is basically. And remember, the stability of alkene has to do with the substitution of the alkene. The more substituted the alkene is, the more stable that alkene is. Does that make sense? That's the Joseph rule. But then we went over and then looked at some exception. One of the exceptions was conjugation. If you have an alkene that will lead to the formation of a conjugate, then the less substituted alkene will be formed. And the reason is simple, is because the alkene that will lead to the formation of a conjugated system is more stable. Remember what a conjugated system is all about. It's an alternation of double and single bond. That's what we refer to as a conjugated system. Another rule, another exception to the Joseph rule is that alkyl fluoride, especially alkyl fluoride, they will lead to the formation of the less stable product as your major product. Okay? And so what we refer to as the less stable product here, that's our alkyl fluoride. So that's the fluoride over, oops, let me use a transparent guy. It looks like my computer is still sleeping this morning. Yeah. So that's our fluoride, okay? And to do the elimination, we have to remove one of the alpha hydrogen or the beta hydrogen. Those hydrogens labeled there, okay? Now, from what we've been doing, this hydrogen is the one that's supposed to be removed because it will lead to the formation of a more substituted alkene. But it turned out that with the chemistry of the fluoride, this is instead a hydrogen that will be removed, the less stable one. And that's what we have here. 1-pentene as being the major product and 2-pentene being the minor product. That's an exception to the rule, okay? That's an exception to the rule. And the reason for the exception to the rule lies at the level of the structure of the transition state. If you look at the transition state formed by 1-pentene, that transition state is more stable compared to the transition state formed when you have to generate 2-pentene. Okay? And that's simply because the fluoride is a poor leaving group. The fluoride is a poor leaving group, so he doesn't want to go. And so it makes the transition having what we call a carbanion-like structure. Okay, carbanion is an opposite of a carbocation. Remember, a carbocation is a positively charged carbon, whereas a carbanion in this case will be negatively charged carbon. Okay, and the order of stability of carbanion is kind of reverse that of carbocation. So that's why the less substituted alkene will be preferentially formed over the more substituted. Okay, because of that negative charge. You can see that negative charge. Remember, I said carbanion tends to have an opposite effect from carbocation, meaning that a primary carbanion is more stable than a secondary carbanion. Does that make sense? And so if you look at these two transition states, the first one goes through a pseudo primary carbanion, and the second transition state goes through a pseudo secondary carbanion. Does that make sense? And so the primary carbanion is more stable than the secondary carbanion. So that's why the fluoride will favor that. So this is a recall of what we just talked about. Carbocation stability. We know that the tertiary carbocation is more stable compared to a methyl or a primary carbocation. And I said the reverse is true when you're looking at carbanion. In terms of carbanion, the tertiary carbanion is less stable and the primary or the methyl carbanion is more stable. Does that make sense? Carbanion is a carbon with a negative charge. So, senior, start thinking of an artwork for carbanion. Yes. So are we good? And so over here we can quickly have a summary of what the leaving group effect is. This is very similar to what we've talked about in substitution reaction. Okay, you have different leaving group. We have different leaving group, and we notice that when you leave from the iodide to the fluoride, you are increasing instability of the leaving group, and then the reaction also goes faster. Does that make sense? So the better the leaving group, the faster the reaction is. That's basically what you guys have to remember here on this table. Okay, the better the leaving group, the faster the reaction, and it follows the same rule as in SN1 and SN2. Now you remember in SN1 and SN2, we said that tertiary alkyl halide will prefer to undergo an SN1 reaction, whereas primary and secondary will prefer to undergo an SN2. So we have something similar happening with the E2 reaction. In the E2 reaction, tertiary alkyl halide will prefer to undergo an E2 reaction easily. So it will be easy to do an E2 reaction with those tertiary alkyl halide. Okay, and that's what we have over here. So our tertiary alkyl halide will react faster than the primary alkyl halide. This is very important. You know what it means by when they say this is very important, right? That's it. That's the meaning of being very important. It means you have a multiple choice question that is testing this knowledge. Huh? Watch the video. Oh, really? Oh, then I'll probably have a mic connected. Okay. Any question, guys? Any question with the E2 reaction? So the E2 reaction is a one-step reaction. One step. In other words, we can refer to that as a beta elimination. Okay? And it only depends on the concentration of the alkyl halide. It doesn't depend on the concentration of the base. Does that make sense? So if you double the concentration of the alkyl halide, the reactions double. If you double the concentration of the base, nothing happens to the reaction. Does that make sense? Because it only depends on the alkyl halide. Now the other guy is the E1. Oh, sorry, what did I just say? I hate this thing. The E2 depend on both the base and the alkyl halide. The E2 depend on both the base and the alkyl halide. If you double the concentration of the alkyl halide and that of the base, then the reaction will quadruple. Does that make sense for the E2? Now we are looking at the E1 reaction. Just like the SN1 reaction. It's a two-step reaction. And the rate law depends only on the concentration of the alkyl halide in this case. So it doesn't depend on the concentration of the base. It simply means that if I double the concentration of the alkyl halide, the reactions double. If I double the reaction of the base, nothing happens. because it doesn't depend on the concentration of the base. Does that make sense? Let's look at the rate law for, let's look at the rate law of an E2. That's the rate law for an E2. Rx stands for the alkyl halide. Rx stands for the alkyl halide, and B minus stands for the base. Okay. Now, question. What if I triple the concentration of Rx and then leave the concentration of the base intact? What happens to the rate of the reaction for this one here? Say that again. It triples. Does that make sense for everyone? Okay, if I triple the concentration of the alkyl halide without affecting the concentration of the base, the reaction simply triples. But what if I triple the concentration of the alkyl halide and triple that of the base? What happens to the reaction? It increased by 9-fold. Does that make sense? So that's the way I want you guys to see that. What if I triple the concentration of the alkyl halide and doubles that of the base? What happens to the reaction? Say it again, Zion. People can't hear you.
You go over to
It's very important. At the end of the day, you guys will know all my exam questions. So the E1 mechanism is a little bit different from that of the E2. It's a two-step mechanism, and it goes through the formation of an intermediate. And that intermediate is the carbocation. The first step of the reaction is the removal of the leaving group. So the leaving group leaves, and then you form a carbocation. Because you're forming a carbocation, everything we said in this class with respect to a carbocation is true. Does that make sense? It means that a carbocation can undergo a rearrangement. It can do a 1,2 hydra shift, it can do a 1,3 methyl shift, a 1,2 methyl shift, and so on and so forth, searching for the more stable carbocation. Okay? Now, next thing you have once the carbocation is formed, your base. In this case, water is acting as a base. Your base comes in and then gets the hydrogen out and forms a double bond in a fast process. And like every reaction that goes through the formation of a carbocation, the formation of the carbocation is always the rate limiting step. Does that make sense? The formation of the carbocation is always the rate limiting step. That's very important again. Right, Zion? Identifying all those steps in a reaction is very important. Very, very. Is James in class? James, he's not. Malik, what happened? You're sitting at the back now. You just abandoned me. Ah, okay. Any observation? Do you see where the trouble can be? Do you see the similarity between E1 and SN1? They basically have the same type of reaction condition. It means that there will be a competition between E1 and SN1. Okay? So whenever you are running an SN1 and an E1, there is always a competition. And that's what I want to see when you guys will be writing your lab report. Those in my group. Those in my group. Okay? You remember when you were doing that SN1 reaction, you had to confirm that the product is that of an SN1 reaction and not that of an alkene. So the question is, what reaction condition favors the formation of an SN1 over an E1 reaction? Okay. We'll not talk about the mechanism by which the base will move that proton. I just need to talk about the reaction itself. Just like an E2, the E1 reaction is also radioselective. The more stable product is formed. Same thing like the E2. Okay, that's radioselectivity. The more stable product is formed. The more stable alkene is the alkene that's highly substituted. In other words, the alkenes whose double bond has fewer hydrogen, smaller number of hydrogen. This is something that we know already. We've talked about this. Again, I said it's a two-step mechanism. It's a two-step mechanism. The first step leads to the formation of the carbocation. Then the second step between the formation of the more stable product and that of the less stable product is a matter of thermodynamic stability. The transition state that leads to the formation of the more stable product. Over here, you can see it. Let me zoom in here. The green transition state is the one that leads to the formation of the second product. You see that transition state is slightly lower in energy compared to the transition state of the guy that leads to the formation of the less stable product. And that's simply because if you look at the structure of the transition state, the one that leads to the formation of the more stable product gives you a partially more stable carbocation compared to the other one. And again, the law of the leaving group follows the same. The law of the leaving group is the same. The iodide is a better leaving group than the fluoride. Okay? So the law of the leaving group remains the same. Iodide is better than the fluoride. And like I said, there's a great competition between this reaction. You can also have a competition between an E1 and an E2 in a reaction. Okay? Now, primary and secondary alkyl halide will preferentially undergo an E2 mechanism, just like the SN2. And then tertiary alkyl halide will preferentially undergo, well, tertiary is a mixture of E1 and E2. But I will be tempted to say that tertiary alkyl halide will most likely prefer an E1 mechanism because it goes through the formation of a carbocation. Okay? Now, if you have a reaction in which that can proceed both by E1 and E2, then chances are that the rate of your reaction will be a combination of the rate of an E1 and that of an E2. Very similar to the exercise we did in the lab. The rate will be a combination of that. Now, for a tertiary alkyl halide, which can undergo both reactions, either an E1 or an E2, the E2 will be favored if you have a high concentration of a strong base. The E2 will be favored if you have a high concentration of a strong base. Remember, strong bases are these bases with negative charges. Okay? Most of these bases that you see with a negative charge, chances are that they are strong bases. OH minus, NH2 minus, and so on and so forth. Those are chances that they will be strong bases. And the E1 will be favored if you have a low concentration of a weak base. Most weak bases are neutral in nature. Water, for example, is a weak base. Any questions so far, guys? Now, in the elimination mechanism, here we are looking more at the SN2. We are looking more at the E2 mechanism now. Okay. You remember we talked about the front side and the back side attack. Here we'll be talking about the anti and the syn elimination. Anti, remember, it means that they are on opposite ends. With an E2 mechanism, the anti-elimination is preferred over the syn elimination. And the reason is simply because the hydrogen on the beta carbon and the leaving group are 180 degrees away from each other. Okay? And so that's a perfect orientation for elimination to take place because they are 180 degrees away from each other. Compared to a scene elimination, okay? And a scene elimination in terms of stereochemistry will correspond to like a staggered conformation, no, eclipse, sorry. The scene elimination will correspond to what we refer to as an eclipse conformation. Does that make sense? And so that will not be favored in terms of elimination. Conformations that are staggered will be favored, 180 degrees from each other. Okay, that's what I want you guys to know. And so this anti-elimination avoids the repulsion of electron between the electron-rich base with the electron-rich leaving group. That's why the anti-elimination is favored. I don't know if that really makes sense to you. Look at the base. Remember that the base is electron-rich. Does that make sense? Remember that the base is electron-rich. And the leaving group also becomes electron-rich when he's leaving. And so if you remove the leaving group from the same direction in which the base is coming, you will have this clash of negative charges. That's why we stop the scene elimination. Does that make sense? So the anti-elimination is favored because the incoming negative base literally does not meet the outgoing leaving group, which is also negatively charged. So they don't meet. And so the reaction can easily take place. Does that make sense? Avoiding all those clashes. And so the E2 reaction is stereoselective. You remember when we talk about stereoselectivity, is the formation, preferential formation of a specific stereoisomer over the other. Okay, that's what stereoselective is. The E2 mechanism is stereoselective, and that's not a surprise, right? The E product will be more stable than the Z product. Why? The E product will be preferentially formed over the Z product, right? Makes sense, right? For everyone who doesn't know why. You don't know why? Look at the E and then look at the Z. You will know why. Do you know why now? Yes. In the E, the bulky group are far away from each other, so it minimizes interaction compared to the Z. Does that make sense? So the E is more stable than the Z. Does that make sense, guys? So the E is like the trans. So an E2 would prefer to form a more stable, and that more stable will be an E product. Is that okay? And so if you look at those anti-elimination, if you look at the anti-elimination, the leaving group are this hydrogen and the bromine. So they are opposite to each other. And by doing so, you also now tend to put the two bulky groups away from each other. You are putting the bulky group trans from each other. So that's how the E product is more stable. If you look at the Z product, by looking at the Fischer projection or the Newman projection of the Z product, you will notice that although the group are anti to each other, the leaving group and the hydrogen are anti to each other, the bulky group will be very close to each other. They are next to each other, and that's not stable. So this is not a very stable Newman projection compared to this other Newman projection. Does that make sense? And the more stable Newman projection will lead to the formation of the more stable product, which is the E. And again, the more stable product is easier to form. You look at the transition state. The transition state that leads to the formation of the E is more stable than the transition state that leads to the formation of the Z. Is that okay? And that has to do with the interaction of those bulky groups. And so, same explanation. The largest group should always be on opposite side. Okay? Once you have the largest group on opposite side, then your chance are that you will always have your major product. So you have the E and you have the Z. That's the easiest way to remember it. The largest group on opposite side. That's the stereoselectivity of an E2 reaction. Now, there might be some exception to this, right? There might be some exception to this. And one of those exceptions is when you only have one beta hydrogen present in your molecule. When you only have one beta hydrogen present in your molecule, it now depends on the way the initial configuration are. You could as well form the Z or form the E. Okay? Stereoselectivity here becomes very important if you have two beta hydrogen. Then there will be a choice to make. The base will choose to remove the beta hydrogen that will lead to the formation of the more stable product. But if you only have one beta hydrogen, there is no choice to make. Does that make sense? If that hydrogen was already pre-oriented in the way that the E product will be formed, then you're bound to form the E product. If that beta hydrogen was already pre-oriented such that you can form the Z product, there is nothing you can do. Your product will be Z. Okay? And what I mean by that pre-orientation, this is what I mean by. If you look at this first carbon here, you look at the bulky group, which is that C6H5, you will notice that the bulky group is in the same plane with the other bulky group here, which is the CH3. They are all on the dash bond. They're on the same plane. And so the product will make them the same. So that's why the two bulky group will end up being the same. Because initially they're already on the same plane. So they are pre-oriented that way. And you only have one beta hydrogen. So it doesn't have the choice. It can only form the Z. But if you do the same analysis with the one up there, you will notice that the bulky group of this carbon, this guy, is in an opposite plane to that one. That's just pre-orientation. There is nothing they can do. They only have one hydrogen. And so because they're already on the opposite plane, they will give you a product in which they're opposite to each other. Does that make sense? Selection only happens if you have the choice between two hydrogens. Which one should I remove? In that case, you will choose to remove the one that will lead to the formation of the more stable product, which is the E. Does that make sense? James, I was looking for you this morning. Are we good with that, guys? And so that one was true for an E2. But in an E1, no matter how the pre-orientation of the starting material is, the major product will always be the more stable one for an E1. For an E1, the major product will always be the more stable one. And I want you guys to be able to understand that. Why is that so for an E1? Why is that so for an E1? Why is the major product always the more stable? Can someone try to read my mind? You have a brain in your people, so you need to think about it. Why? What is different between an E1 and an E2 in terms of their mechanism? In terms of their mechanism, what is the difference between an E1 and an E2? The E1 goes through the formation of a carbocation, right? And so if you go through the formation of a carbocation, the molecule becomes flat. Remember the same story with an SN1. In terms of stereochemistry of an SN1, we say you can have inversion and retention because the carbocation is flat. And so if the carbocation is flat, it doesn't matter. In that case, it will choose the structure that will lead to the formation of the more stable product. Does that make sense? In the E2, it's a one-step mechanism, so the orientation is important. With the E1, it doesn't matter because you're going through the formation of a carbocation. Okay? And that's the carbocation here. Once you form that carbocation, now it will just lead to the formation of your major product, which is the E. It will preferentially choose to do that one. And so we have a summary of the stereochemistry here of all the reactions we've talked so far. Stereochemistry of an SN2, E2, SN1, and E1. Okay, this is good for you to go and read. That's a summary of all the stereochemistry. So we are looking, this is a quick review again. Now let's look at specific cases. Let's look at a cyclohexane ring. You remember on a cyclohexane ring, we have different types of bond. We have the axial bond and we have the equatorial bond. I know you remember that. The axial bonds are the one that points either straight up or straight down. Those are the axial bonds. And the equatorial bonds are the ones that points away from the molecule. Okay, away from the molecule. And so if you want to carry out an E2 reaction, if you want to carry out an E2 reaction on the cyclohexane ring, that E2 reaction can only take place between two atoms that are on axial bonds. Does that make sense? The reaction is faster if the atoms involved in the elimination are axial to each other. I want you guys to take note, okay? So long as those groups, the leaving group and the beta hydrogen are axial to each other, then an E2 elimination will be favored. And that's what we have here. And the reason is simple. Once they are axial to each other, it makes them 180 degrees from each other. It means they are anti to each other. And we just said that anti is favor over syn elimination. Does that make sense? So the both group being axial makes them anti, and so the elimination will be faster in terms of an E2 mechanism. And that's basically what we're talking here. So both groups must be axial. In this case, the leaving group is chlorine, and the other guy, the leaving group is chlorine and the hydrogen is axial. So both of them need to be axial for elimination to take place. And once they are axial, you can now eliminate to form your double bond. Does that make sense? If one of the group is equatorial, the other group is axial, the reaction will be slow. If both groups are equatorial, I don't even think the reaction will take place. Does that make sense? And so the rate constant of an elimination reaction in the cyclohexane is proportional to the equilibrium constant. Remember, equilibrium constant has to do with stability. Okay? Equilibrium constant has to do with stability. Now, the equilibrium constant for a cycloalkane is given by the concentration of the more stable conformer divided by the concentration of the less stable conformer. Okay? Now, for a reaction that takes place through a more stable conformer, then your equilibrium constant is large. And then for a reaction that takes place through the formation of the less stable conformer, it means that your equilibrium constant is small. And if the equilibrium constant is small, it means that equilibrium will have to shift for that reaction to take place. There will be a movement in the equilibrium. And so that's what we're looking at here. We have two conformations over here. We have a more stable conformation versus a less stable conformation. Now, let's do a review of 301. What makes the other conformation less stable? What makes this conformation less stable? Say again, you guys. The bulky group is in the axial position. Does that make sense? This is our bulky group. That bulky group is in the axial position. If it is in the axial position, then what happens? We have the 1,3 diaxial interaction. Does that make sense? Because there's this hydrogen pointing downward here. So there's an interaction between those two groups. Okay? That's what makes it less stable. At the same time, if you look at this now, you will notice that our chlorine here is in an equatorial bond. The chlorine is the leaving group. The chlorine is the leaving group. It is in an equatorial bond, which is not good. Because for this thing to take place, the leaving group must be in the axial. Does that make sense? And so, we will have now to rearrange to a more stable conformation in which the chlorine now gets to the axial position and the bulky group in the equatorial. And so the chlorine now becomes axial to the hydrogen and elimination can easily take place. That's basically the literature was singing above by saying that equilibrium is large and blah 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 blah. So does that make sense? I'm happy you guys still remember your stereochemistry. Remember over here again, we said if your Ke is small, meaning that the less stable conformation is present in more quantity than the more stable, then your equilibrium constant will be small. We will now explain that scenario with this example over here. We have our 2-cyclohexane ring. We have the more stable because both groups are equatorial. That's the more stable because both bulky groups are equatorial. And this one is less stable because both bulky groups are axial. But then, although this is less stable, because the chlorine is in the axial position, it will easily react with this hydrogen that is also in the axial position because that is the conformation, the preferred conformation for elimination. Okay? And so with this kind of elimination, you will see that this reaction will be a little bit slow. Does that make sense? This kind of reaction will be slow. And the reason is simple. Because the conformation that leads to the formation of the product is not the more stable conformation. I don't know if it makes sense. So it will give time for the more stable conformation to transform to the less stable, which kind of go against the rule, right? Because things will prefer to always be stable. But in this case, for this reaction to take place, the more stable will have to transform to the less stable conformation before the reaction takes place. Does that make sense? All you need to know in order to remember this is that the leaving group and the hydrogen need to be axial to each other. Does that make sense? They need to be axial to each other for the reaction to take place. And so E1 on the 6-member ring, the guy doesn't matter. He doesn't care. E1 doesn't care whether you are axial or not. And the reason is simple. Because it goes through a carbocation. So long as you can leave, that's fine. Then we can take place. If he has to go through an E1. Okay? For an E1 mechanism, it doesn't matter whether both of them are axial or whatsoever. It doesn't matter. Once the leaving group is there and then it leaves, then things can happen. I remember that for an E1, you need to have a tertiary alkyl halide, okay? If you have a secondary alkyl halide, it cannot undergo the E1. The secondary alkyl halide can only undergo E2. So take note about that. Competition between SN2 and E2 reactions, okay, of the alkyl halide. Remember we talked about it. Now, in an SN2 reaction, we said the primary and the secondary alkyl halide will prefer to go through an SN2 reaction. Okay? Whereas in an E2 reaction, the tertiary and the secondary alkyl halide will prefer to undergo an E2 reaction. So we have kind of a reversal there. If you are doing a comparison between an SN2 and an E2. Okay? Now, another interesting comparison, the one we have to look at here, is, well, this one just shows us. We have to look at that SN2 reaction here, the effect of the base and everything. Okay. Here we talk about the effect of the base. In an SN2 reaction, the base is referred as a nucleophile. Okay. Now, if you have a steric base, meaning a bulky base, a very big base, in that case, elimination will be favored over substitution. Does that make sense? So if you have a competition between SN2 and E2, but the size of your base is big, then elimination will be favored. And that is illustrated over here. We have CH3, the methoxy group, as our base. That's a small base. And we are comparing it with this other base here, the T-butoxide. That's a bulky base. Okay. Now, that bulky base will favor the elimination product. The bulky base will favor the elimination product. And then the small base technically favors the substitution product. But be careful. It's supposed to favor the substitution product. My question is, why is the elimination product favored over there? Can someone answer it to me, please? Well, the answer is even there. Oh, God. That's the answer. If you compare this is sterically hindered. You have this thing present there. And if it is sterically hindered, it will prevent the nucleophile from connecting. So that nucleophile will instead prefer to be a base. Okay? So steric hindrance, whether of the nucleophile or the alkyl halide, will lead to the formation of the alkene, elimination product. So if you're comparing an SN1 as an SN2, take note of the bulkiness of your group. The strength of the bases. The substitution reaction is favored by a weak base, whereas the elimination reaction is favored by a strong base. And you remember what we talked about, the weak base and the strong base. Okay? A strong base is negatively charged. That's one way you can remember it. And then a weak base means it's a stable base. Does that make sense? If you're a weak base, it means you're a stable base. And now here we have two bases. Let me label them. We have two bases. Let's call this one base A and base B. Destiny, you know my question, right? What's the question? Yeah. What's the question? What's the question? Which one is more stable? Right? Remember I said the weak base is more stable. The weak base is more stable. Which one is more stable? Which one? A. Do we all agree that A is more stable? Why is A more stable? Resonance. Because A can undergo resonance. That's why A is more stable. How do we know that something can undergo resonance? X equals to Y minus Z, and then the star is the negative charge. You remember that? And our star is a negative charge in this case. So, that A can undergo resonance. Because A can undergo resonance, it makes A more stable. And if A is more stable, then A is a weak base. And if A is a weak base, then A will prefer to undergo substitution. Does that make sense? Are we on the same track, guys? Okay. And this kind of substitution here, for those of you that will be doing biochemistry, that's basically the way enzymes react. Okay, they like to undergo that kind of substitution in enzymes chemistry. And talking of which, by the way, there will be biochemistry this summer. I will be teaching biochemistry this summer. So those who want to go on break, we will meet. Those who don't want to go on break and stay here with me, yes, we will meet. Oh, you'll be around. Malik, you'll be around, right? Why? Yes. Okay. So the take note message is that if your nucleophile is stable, your nucleophile is a weak base. And if your nucleophile is a weak base, then he will prefer to undergo a substitution reaction. Does that make sense? Already we mentioned it, right? That steric hindrance favors elimination. So a bulky base will favor an elimination reaction. Whether a bulky base or a bulky alkyl halide, all of them, so long as it's bulky, it favors an elimination reaction. And so these are two examples of bases that are really bulky. DBU and DBN, those are examples of really bulky bases. So they will favor an elimination reaction. This is just for your information, how that bulky base reacts. We don't need to worry about that one. High temperatures will favor elimination reaction. High temperatures will favor elimination reaction. So if you run a reaction at a low temperature, you'll be able to form a little bit more substitution product compared to running the same reaction at a high temperature. In that case, you will form an elimination reaction. And again, we'll talk about the reason why high temperature favors elimination reaction. Okay? It's because elimination leads to an increase in entropy. You remember what entropy is? State of disorderliness. Okay? Elimination, you are leaving maybe from 2 reactants to 3 products. So you are increasing in entropy. And so to overcome that increase in entropy, you have to kick the reaction. So that kick is there to overcome the increase in entropy. Whereas the substitution reaction, the entropy virtually remains the same. Substitution, if I start with 2, I will end up with 2. So the entropy change is 0. Does that make sense? So I don't need to kick, I don't need to overcome. Does that make sense? Yeah. That should give you ideas, right? Based on what we did in class already. If temperature favors elimination, when you did your reaction in the lab, SN1 and SN2 reaction, did you guys kick that reaction? Did you apply the heat? No, are you sure you applied the heat? When you did the reaction, did you guys apply heat on the reaction? No, you didn't apply heat. All you had to do, you took your alcohol, then mix it with the acid, and then shake it in the corner, and the product was formed without actually heating it. So that's how you were favoring substitution over elimination. Does that make sense? You were favoring substitution over elimination. And so when you did that, when you were shaking that thing, what was the nucleophile? What was the nucleophile? The nucleophile was Cl minus, which is a weak base. Does that make sense? The nucleophile was chlorine because the hydrochloric acid, you remember the hydrochloric acid you used? Yeah, that hydrochloric acid, you were replacing the OH group with the Cl. And so that Cl minus is a weak base because hydrochloric acid is a strong acid. And so that Cl minus becomes a weak base. And if it's a weak base, in this class we just said it, weak base favor a substitution. Does that make sense? So those are the kind of stuff I want to see in your discussion. In that case, you are like telling me that you know what you're talking. So that's how you will be able to say that this reaction we actually did in the lab, we were favoring substitution over an elimination reaction. Does that make sense? Now, is it an SN2 or an E2? If it's a tertiary alkyl halide, we know that tertiary alkyl halide do not undergo SN2. So if you have a tertiary alkyl halide, the only product you can form will be an elimination product. Because tertiary alkyl halide do not undergo SN2. Does that make sense? Now, another comparison. We're done with SN2 and E2. Now we are comparing SN1 and E1 over here. Okay. Now, remember, we're looking most likely at the tertiary archihalite because the tertiary archihalite can undergo both elimination and substitution, E1 and SN1, okay? And they all go through the formation of a carbocation. Now, if you use water to run the reaction, water will give you a mixture of product because water can act as a base as well as a nucleophile. Then we'll look at those conditions that favors one over the other. Again, when you have a weak base, SN1 and E2, substitution is favored. Does that make sense? If you have a weak base, substitution is favored. Again, I will quote the example that we had in the lab. Our base was a Cl minus, and Cl minus is a weak base, and so it favors substitution. But if you have your strong base in there, chances are that you have an elimination product. Okay? If you have a strong base, chances are that you have an elimination product. And these are two examples. This is my nucleophile, which is an alcohol. An alcohol, technically, if you want to look in terms of bases, is a weak base compared to an alkoxide. This is ethoxide, which is a strong base. Remember that negative charge. If you don't know it, remember it. That negative charge compared to a neutral molecule, that negative charge is strong. Does that make sense? Because in this case, you are doing a comparison between this guy who is neutral and that guy who is negative. The negative charge is strong. And so, because you are strong, you will lead to the formation of an elimination product. Well, after preaching, that's a summary of similarities and differences between the SN1 and the SN2. And should I continue teaching, Alicia? Okay, life is good. I'm not even sure the other section will get up to this point. So let's stop here, right? So on Thursday, we'll be having a review session. I posted a try your hand on Blackboard. I think I did, right? I posted a try your hand on Blackboard. It has a couple of multiple choice and short answer questions. So I will go through that on Thursday in class, and I'm sure we'll not finish it in class. So I will finish that during my lab session. And during your lab session also, you guys will go through it. During your lab session. And the review of Thursday morning is not for you to learn new material. Because you'll be having the exam in the evening at 6 o'clock. So by the time you come here on Thursday morning, you should be ready, actually. You should be ready. Does that make sense? 6:30, yeah. 6:30.